Hey everyone, and welcome. Today, we're going to strap in for a pretty incredible journey to the really mysterious outer frontiers of our own cosmic backyard. We're heading to the solar system's deep freeze to explore two of its largest and, honestly, most enigmatic structures.
So, we all know the planets, right? But what happens if you just keep going? What's out there in that vast, dark expanse just past the final gas giant? Well, that's exactly the question we're tackling today. Okay, let's dive in.
You know, astronomers sometimes call this whole area the third zone of the solar system. First, you've got the inner rocky planets, then you have the outer gas giants, and then you have this, a huge realm of icy leftovers from the very dawn of creation. Our trip today has two big stops. First up, we'll visit the Kuiper belt, and you can kind of think of it as the solar system's sprawling suburbs. After that, we're going to venture out way further to the Oort cloud, the real, true boundary, the very edge of the sun's gravitational kingdom. So let's kick things off with our first stop, which is the closer of these two immense regions, the Kuiper belt. I mean, this is a place that was just a theory for decades, but now we know it's a huge piece of the puzzle for understanding how our solar system even got here. Okay, the key phrase to remember here is icy leftovers. Just like the asteroid belt, this is a whole region of primordial stuff that just never quite managed to pull itself together into a planet. And while it's named for Gerard Kuiper, who first theorized it way back in 1951, you'll also hear some scientists call it the trans-Neptunian region, which is, a bit more descriptive. Okay, so to really get a handle on this, let's compare it to the asteroid belt, which we're all a bit more familiar with. And the differences are, well, they're huge. The Kuiper belt is way farther out. It's made mostly of ices instead of rock, and it's not a thin little belt. It's this big, thick, puffy donut shape. Oh, and it's also vastly larger and more massive. And when we say further out, we really mean it. An astronomical unit, or AU, is the distance from the Earth to the Sun. Neptune hangs out at about 30 AU, and that's right where the main part of the Kuiper belt kicks off, stretching all the way out to about 50 AU. Yeah, we are a long way from home already. So, what's actually in this giant cosmic donut? Well, an absolutely incredible amount of stuff. We're talking millions of small, icy bodies. There are hundreds of thousands of objects over 100 kilometers wide, and of course, this is home to its most famous resident, the dwarf planet Pluto. All of it made of rock and frozen stuff like water, ammonia, and methane. But here's the thing. The Kuiper belt isn't just some random mess of ice and rock. Nope. It's got structure. It's got an architecture. And the grand architect? That would be our eighth planet, the gas giant Neptune. You see, Neptune's massive gravity acts like a kind of cosmic shepherd. It's constantly nudging and pulling on all those icy bodies, sorting them and organizing them into different groups, or what we call families. Its influence is, without a doubt, the most important factor in shaping how the whole belt is laid out. And this gravitational sorting creates what we can think of as three main families, or maybe even neighborhoods, of Kuiper belt objects, KBOs for short. First, you have your classical KBOs, which are far enough out that their orbits are nice and stable. Then you get the resonant ones, which are locked in this incredible gravitational dance with Neptune. And finally, you have the scattered objects, which got a little too close and were basically kicked by Neptune into these wild, eccentric orbits. Now, that's all possible because of this fascinating concept called orbital resonance. It's basically a stable repeating pattern. The easiest way to think about it is like two dancers moving in perfect, synchronized time. For instance, a KBO in a 3-to-2 resonance with Neptune will circle the Sun exactly 2 times for every 3 trips Neptune makes, and that perfect timing keeps him from ever getting too close. And you know who the most famous example of this is? Pluto itself. It's locked in that very same 3-to-2 resonance with Neptune. But it's not alone. There are actually so many other objects caught in that exact same orbital dance that astronomers give them a fantastic name, the Plutinos. All right, so we've toured the solar system's suburbs. Now, it's time for the great leap outward. We're going to a place so vast it's honestly hard to wrap your head around. So get ready for a serious sense of scale. Remember this number, 50 AU. That's where we are right now, at the far edge of the main Kuiper belt, 50 times farther from the Sun than we are here on Earth. That feels pretty far out, doesn't it?
Okay, I want you to hold on to that feeling, because now we're going to go 2,000 times further.
That's right, 100 100,000 AU. That's the outer edge of our next stop, the Oort cloud. We're talking about a distance of over a light year. It's so far that it could stretch about a third of the way to the next nearest star. Just mind-boggling. Now, unlike the Kuiper belt, which is kind of flat like a donut, the Oort cloud is something else entirely. It's this theoretical, giant, spherical shell of icy stuff that surrounds the entire solar system. It envelops everything, the sun, all the planets, even the Kuiper belt. This is the true edge of our solar system. So let's just break down the key differences, because they're huge. The Kuiper belt is a relatively flat donut, kind of on the same plane as the planets. The Oort cloud, on the other hand, is a giant sphere, with objects coming in from every possible direction. And the difference in scale, well, it's just staggering. So you might be wondering, why should we care about these incredibly distant, freezing cold regions? Well, here's why it matters. Because this is where some of the most spectacular visitors to our night sky are born. We're talking about comets. So the connection is actually pretty simple. These two different regions produce two different types of comets. The Kuiper belt is the source for what we call short-period comets, the ones that pop into the inner solar system pretty regularly, every 200 years or less. But the Oort cloud, that's the home of the long-period comets, these cosmic ghosts that might only swing by once every few thousand or even millions of years. I mean, just let that sink in for a second. Comet Sighting Spring, which flew past Mars back in 2014, won't be back for another 740,000 years. The last time that comet swung by our entire species, we weren't even here yet. That's the kind of timescale we are dealing with when we talk about the Oort cloud. And really, what this all leads to is a huge shift in perspective. Our little neighborhood of planets, this warm, cozy, well-lit zone that we call home, it's the exception. It is not the rule. The rule in our solar system is the vast, cold, dark emptiness of the Kuiper belt and the Oort cloud. It's a pretty humbling thought, isn't it?